Let's go through another truss example with the method of sections, and then what time's it getting to be? We'll take a little break. Get your mind's rest a minute. We're going to look at the same truss just so it's easy. Same truss, same exact truss. But we're going to use a different method to figure out what the loads are inside. And I think this method perhaps a little easier. More useful, I'll say, not easier. First thing we do, we're going to get rid of these guys. We all know that by now. Very, 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 very first thing. It's going to be more important with the method of sections than it is method of joints. And we decided last time this was what, 750 pounds? What was the other side then? If we've got 1,000 down and 750 up, we've got to have an extra 250 up, right? So I want to know what the load is. Well, what's the first thing that I can do? I can get rid of this guy, right? Because that's the stem of the T. Maybe it'll make it easier for my problem. Maybe it won't. I want to know what the load is in that guy there. Now I can go through a bunch of method of joints and do that joint just like we did before to find what this load is. Then I can go through the method of joints again at that point to figure out what this load is. And then the method of joints again at this point to figure out what that load is. Or what I'm going to do is split this truss right here. So I am essentially going to just erase the rest of this truss. No reason I can't do that. If I replace all of what I had before, what I'm erasing with loads. Boom, it's gone. And the dimension of this point, well, we got 20-foot base, so this is 40 foot. And I'm going to have a little load here somewhere, just replacing loads where I cut the truss off. So I want to know what load is. It's kind of like the method of sections we just talked about. I've got 250 pounds coming up. I've got this crazy diagonal right here. And I want to replace that with an up and a down and a left and a right. So I can replace that just like I did before. Excuse me. With a vertical and a horizontal, and it ends up being the exact same problem it did before. This is 250, so I got 250 going down, I got 250 coming up. This is a 1-to-1 ratio, so this has got equal to 250. I then have to go back to my diagonal. What's my diagonal load? Well, it's going to be coming down this way. 250 times square root of 2, because my little ratio here is 1, 1, square root of 2, 250 square root of 2. I don't know if I had that written down or not. What does that equal to? $353 pounds. So let's say instead of finding the load in this member, they wanted the load in this member. Can I use the method of sections to figure that out? We sure can. Let's get rid of some of this stuff first. Okay. What we're going to do is we're going to take this whole truss and we're going to figure out moments about this imaginary point. Even though we don't have members connecting it, we do have loads that still go through that point. So we're just going to look at it clockwise. About point A. What would that be? Well, it'd be this 250 pounds times the 40 feet. It doesn't really matter that this 250 is offset down here. We can move that 250 anywhere along this line we want. So the 250 could just as easily be acting right here than it is down here. So 250 pounds times that 40 feet is clockwise. I don't have anything else that could possibly... This load, we're not sure what the direction is. But it's going to have to make it go counterclockwise. Because if it went clockwise, there wouldn't be anything to counter it. So counterclockwise would mean the whole thing's rotating in this direction, which means the arrow wants to be that way. Counterclockwise is equal to whatever we're looking for, we're not sure yet, times how far? 20 feet. $250, 40 feet is equal to something times 20 feet. Algebra, high school algebra. 250 times 40 divided by 20 is equal to 500 pounds. Tension in that bottom member.